Good morning and good afternoon, everyone. This is Jing Feng. I'm going to host today's TrustML seminar. Today we are very happy and honored to have our valuable guest, Dr. Yue Gao, from University of Wisconsin Medicine. He's a PhD in computer science, focused on machine learning, security, and system security. His work is on adversarial robustness of real-world machine learning system. Hi, Yue. Please get started with your talk. Thank you very much.
Okay, thanks for the introduction. I'm happy to introduce our recent work about the vulnerabilities of preprocessing in adversarial machine learning. So I want to start this talk with the common threats to machine learning models in the literature. So this is a simple pipeline of the machine learning model, its training data, and a potential adversary. So one of the most common threats to the model is the evasion attack, where the attacker can send malicious inputs to the model and cause a miscalculation. And other threats include poisoning attack, which injects poison data to the training set and controls the model's behavior. And there are the inference attack, which infers if a particular sample was used for training. And then there are the extraction attacks, which steals the private and valuable model with cheaper API calls. And to narrow down the problem in this talk, I will focus on the evasion attack. But even corresponds to this evasion attack, there are several different defense approaches. For example, there are robust learning, which is more on the model side, where we want to do adversarial training of the model. And there are also preprocessing defenses, which are kind of the most popular class of defenses in the research community. And as we will cover later, one of the earliest defenses against adversarial examples are actually preprocessing defenses back to the year of 2018. And today, one of the most effective defenses at the year of 2023 are still preprocessing defenses. So we wonder why this class of defenses is so attractive. And they are attractive because they're simple. And they're out of the box. We can simply take one defense and deploy it to any model without doing any actual training of the model. And they're also more efficient than robust learning. We only need to do the inference, and there's no need to adversely train the model. And these are all the benefits of preprocessing defenses. But due to the nature of security, it's very unlikely that these defenses are perfect and will not be broken in the future. And in fact, as we will show, these defenses can have limitations from different perspectives. First, and perhaps the most notorious limitations, is the endless cat and mouse game. When we as a defender want to design defenses for a model, we need to show that our defenses is robust to certain attacks. And the current literature has investigated significant effort into this direction, such as adaptive attacks, which are specialized attacks designed to evade the defense, and also detecting attack failure, so that we are forced to evaluate our defense with a stronger adaptive attack. However, all these solutions cannot guarantee that we are using the strongest attack. So the game is still ongoing and unlikely to stop. That means it's still possible for someone to propose defenses that are robust to some attacks, but only getting broken in the near future. And this is one major limitation, but not the whole story. There can be a bigger issue when we realize that we have only considered an ideal pipeline that is far simpler than the real world. In the real world, the machine learning pipeline is more complicated, and all existing defenses have omitted that complexity. For example, if we also consider the data processing procedure before the actual machine learning model and its defenses, it's unclear to us what does it mean for data processing to be vulnerable. And right now, there are only independent defenses to protect either the machine learning model or the data processing procedure, but not as the whole system. And because the attacker is free to exploit more than one vulnerabilities in this entire system, these defenses that are designed to protect each component could still be compromised. So that's the pipeline, and now let's start with the standard data processing. In this part, I will introduce the vulnerabilities of data processing and explain how that vulnerability would affect the entire machine learning system, given that we have already known that the machine learning model itself is already vulnerable. So as we have discussed, machine learning models are vulnerable to adversarial examples. And to mitigate these problems, there have been several different types of defenses, such as adversarial training, randomized smoothing, pre-processing, post-processing, and detection defenses. But we should come to realize that a machine learning model alone is not a system in the real world. For example, in the real world, not all images match the model's input sites. That means machine learning model is only part of a larger system that at least includes some pre-processing steps, such as downscaling. But this could cause some new problems. For example, the security community recently found that just like machine learning models, the scaling function itself that precedes the model can also be attacked. That is, the adversary can hide a small target image, like a cat, into a larger source image, like a coffee. As a result, the coffee will simply change into a cat after downscaling, and therefore failing the downstream model, because it is a cat. And in this example, what we see from the attack image is a coffee, that the model will only receive a cat image after scaling. And to gain some more intuitions, we can switch to this simplified demonstration. From here, we can see how the pixels of the smaller target image are hidden into the larger source image, and finally leads to a run prediction. And all this happened because the scaling function might only look at a few pixels in each sliding window during the downscaling procedure. And this attack is practical because it can infer the scaling function and its potential parameters with only black box queries. And this knowledge is usually persistent because deployed systems do not change them frequently. And again, there are many defenses that worked pretty well, even against strong adaptive attacks, like median filtering, randomized filtering, or first downscaling the image and then upscaling it. And so what is the problem of these defenses and evaluations? If we look at the border view of the entire machine learning pipeline, we can notice that all these defenses, either for scaling or for machine learning models, are all designed independently for each component. As a result, defenses can actually get surprised when we consider other components. On the left-hand side, scaling defenses could get surprised that the model behind them can be fooled without a clean image from different class. While on the right-hand side, machine learning defenses could get surprised that the scaling function before them can be attacked to hide perturbation. And in all these cases, these defenses could get surprised because they all hold some unnecessary strong assumptions. For example, when the scanning attack only injects clean images from a different class, their defenses make the same assumption, that any attacks on the scanning procedure will only inject clean images. While on the other hand, when the machine learning attack only perturbs the exact input, their defenses still make the same assumption, that no matter how the adversary perturbs the image, we can always observe it. Well, we're not going to blame these defenses. It is important to think about what if the adversary wants to exploit these vulnerabilities together. And following that question, we propose the scanning-aware black box evasion attacks. But how do we make black box attacks scanning aware? At a first glance, we might want to simply combine these two attacks. For example, we can first get traditional low resolution adversarial example using some black box machine learning attacks, and then invoke the scanning attack to hide these pre-generated adversarial examples, for example, into some larger source images. But this strategy does not work well because the scanning attack does not even know what are adversarial examples. So it can easily break the adversarial perturbation when modifying the pixels, like hiding into the larger source image, especially when it wants to evade some defenses. And in this case, even if the scanning attack works, the downscaled image is very hard to remain adversarial to the machine learning model. Then we tried adapting existing black box attacks to the entire pipeline, for example, by taking the end-to-end pipeline as a new giant model. But again, directly adapting existing attacks to the full pipeline cannot exploit the vulnerability of scaling by itself. That means simply attacking the full pipeline does not give us any benefits. To solve this problem, we take a close look at typical black box attacks, and in particular, typical decision-based black box attacks. And we find that these attacks actually have a loop of 3 steps. First, they find a point near the decision boundary. And the second, they sample the noise around this boundary point to estimate gradients of some particular object function. And finally, they use these estimated gradients to update the boundary and to update the boundary point and find a better solution. And as we can see from these steps, step 2 is the only place where we can incorporate the vulnerability of the scanning procedure, because it is the only place that handles the gradients. And this leads to our main technique, the scanning-aware noise sampling. Our sampling technique is derived from 2 observations. First, we know that the vulnerability lies in the low-resolution space, which is the gray plane on the right-hand side, defined by the scanning function and potential defenses. The second, to attack the full pipeline, we still need to sample noise in the high-resolution space, which is the entire ball on the left-hand side. But if we directly sample noise in the high-resolution space, like what existing attacks have done, you might be able to notice that the probability of satisfying these 2 observations is actually 0, because most of the sampled noise will simply lie outside the gray plane. And to overcome this challenge, we choose to sample noise directly in the low-resolution space. First, we find a low-resolution projection, and this is feasible because we can infer the scaling function and its parameters with black box queries. And after that, we will directly sample noise in the low-resolution space so that we have some exploited noise to start with. And finally, we will project this noise back to the high-resolution space. As a result, we can now sample noise in the high-resolution space, but in the meanwhile lies on the vulnerable low-resolution space. And this noise will allow us to exploit the scaling functions, scaling defenses, and plug into existing attacks. But the challenge is, how do we inverse this projection? A straightforward approach will be to minimize the distance between the high-resolution space, the high-resolution noise that we want, and the low-resolution noise that we sampled. However, this is impractical because in this case, we will need to solve this complicated optimization problem for, say, thousands of noise sampling at every attack step. And to overcome this challenge, we need to make another key insight that, in fact, it is unnecessary to have a precise solution for noise that we sampled at random. And this insight shows that there might be an imprecise but much more efficient approach. And that is the gradient of the object function. Well, the previous object function tells the vulnerable direction, and the gradient encodes the vulnerability into the noise. And now with this approach, we can reduce the cost from, say, thousands of gradient descent to only 1 backward pass. And the last step, we need to incorporate defenses that are designed to protect the scanning function. For median filtering, although this defense was designed to protect the scaling function, like a smooth out the noise, but the median function's robustness to outliers actually make the convergence of black box attacks much slower. And as we can see from this example, when black box attacks search for a boundary point using the gradient of the median outputs, they will only increase the perturbation without changing the median function's outputs. And to mitigate this problem, we approximate the median function by a weighted average of the inputs so that its gradient is more amenable for the attack. For this end, we design the weight such that the inputs closer to the median gets larger gradients, and the total number of changes is limited by a certain quantile. And finally, when evaluating randomized defenses, we have to spend more queries to approximate the expectation of the full black box pipeline. And to avoid this additional queries, we reformulate this question to an offline procedure that estimates the expectation of only the randomized preprocessor. And this is possible because we can derive a closed form solution for the composition of the scaling function and the randomized defense. And with this technique, we can reduce the cost from, say, 20 queries of EOT to only one query. and the OT is calculated offline without any queries to the online model. So all these techniques allows us to finally design an end-to-end attack on the entire pipeline and allow us to evaluate what does it mean for the attacker to exploit multiple vulnerabilities in this system. First, on the scaling side, we can evade 4 out of 5 scaling defenses that were designed to protect the scaling function. For example, traditional scaling attack have some artifacts in the spectrum image that we can see some peaks in the spectrum. But our attack avoids that within the same threat model. And then on the black box attack side, we integrate our technique with 2 different attacks and test them on the ImageNet dataset with a ResNet model. As we can see from the green curve, attacking the full pipeline converges much faster. That is, given the same query budget on the x-axis, our new attack produces less perturbation on the y-axis. And in fact, we are even able to achieve similar perturbation as the original attack with about 20K fewer queries. And in particular, from the orange curve, you can see that blindly attacking the full pipeline without our technique has no difference from attacking the standalone model. And if we instead look at the perturbation budget on the x-axis, again, attacking the full pipeline achieves much higher success rate on the y-axis. And in this particular case, our high resolution attack with 10K queries, which is solid black curve, already beats the vanilla attack with 20K queries, which is the dashed red curve. And finally, we test this new attack in the real-world image analysis API, where we have inferred using black box queries that this API actually uses OpenCV's linear interpolation for the downscaling. And after knowing this, when we attack the full pipeline, including the scaling and the model, the performance is much better than attacking only the model in a traditional way. And this shows that attacking the full system is much more practical than attacking a standalone model, even if that model is hidden inside the black box API. And we also compared our joint attack with a sequential variant that first generates adverse examples and then hides that into a larger source image. And when there's no defense, the joint attack is consistently better than the sequential attack. And this shows that simply combining 2 attacks does not work well. And when there is the median filtering defense, while the joint attack still converges faster, the sequential attack becomes worse when it wants to hide optimized adverse examples under the median filtering. And this shows that simply combining 2 attacks might be even worse under certain defenses. So what does these results tell us? These results can show some recommendations for the research community. First, we should be cautious about unnecessary assumptions. And this is because while attacks are free to make any assumptions to make them appear stronger, these assumptions could actually be a bad practice for defenses. For example, being only needing to inject clean images is actually a very strong attack, but a good defense should perhaps avoid this assumption. So when designing defenses, we should always consider the strongest adversary in our threat model. And more importantly, we should be careful if the adversary could potentially exploit multiple vulnerabilities and amplify their threats. And right now, we have only talked about scaling, but there's a follow-up work showed that they can actually extract any preprocessor and attack it. But those preprocessors may not have a severe vulnerability that will allow you to hide perturbation like scaling. And second, we should try to fix bugs, but not attacks. And this is particularly important in the security context because attacks are in fact potentially weak exploits of a critical bug. For example, from the bug scaling, we talked about previous weak exploits that inject clean images and our more subtle exploits that inject adversarial perturbation. But all these exploits remain in the same threat model, which is following the black box machine learning model. As a result, fixing weak exploits could give us a false sense of security. And this is a similar lesson that we have learned a lot from defending against adversarial examples. But for scaling, we can fix this bug because it has closed form solution. But for adversarial examples, the problem remains open. Now, let's assume that we have fixed all these vulnerabilities in the data processing or the standard data processing steps, and we go back to the traditional defensive pre-processing. And a fun fact here is that all preprocessors that you can come up with within an hour have all been published and broken. So people start putting their beliefs in randomized defenses or stochastic preprocessing defenses. And these defenses are indeed harder to break or even harder to evaluate. But in this part, I'll explain their fundamental limitations and why they should not work without evaluating them. And as we have talked about, machine learning models are vulnerable to adversarial examples. And to mitigate these problems, right now people have proposed many defenses. And one popular category of defenses is this stochastic preprocessing defenses. For example, a defender can pre-process input images with a randomized transformation, like random rotation, before feeding them to the classifier. And the intuition behind the defenses is that they want to constrain the attacker so that a successful adversarial example must generalize to all potential transformations at a test time. But the question is, does this strategy really make the adversary any harder? Okay, so there's a question. So this question about research is a good research direction that instead of preventing attacks totally, we should increase like exponentially the cost of the attackers. That's that's totally true. Right now it seems very hard to really increase the cost of the attackers, like you mentioned exponentially. So in cryptography, we can prevent the attack because we can indeed increase the cost exponentially. But right now, it seems hard to connect cryptography with adversarial example defenses. So I think we should look for both ways. But right now, people are still looking at preventing attacks and not increasing the attacker's cost. Yeah. So to answer this question, that whether this strategy really make the attack any harder, we need first to understand how these defenses are evaluated in the literature. And in the literature, their evaluations mostly rely on adaptive attacks, a stronger notion of attacks that incorporate the defense into the attacking procedure. And up to now, we have experienced about 4 rounds of cat and mouse game. And the first round includes some simple transformations, like random recropping, random rescaling, but they're broken in 1 year. And second round includes some slightly more complicated techniques, such as random mix-up or random pixel dropping. And again, they're broken in 1 year. And after that, there comes the BART defense, which randomly assembles 25 transformations, and each one of these transformations itself is also randomized. And this time it took about 3 years to break this defense. And finally, last year, there was the pure defense, which is a defense using diffusion models trying to purify the adversarial perturbation. And we don't know yet when it will be broken in the future. But from these 4 rounds, it seems that we have developed a steady progress where we first design defenses and then evaluate them with adaptive attacks. However, there are some lessons that we have not learned from adaptive attacks. First, adaptive attacks are becoming hard to design and evaluate. For example, the bar defense was only broken after 3 years and actually on a smaller scale dataset, which is a 10-class subset of ImageNet, because the authors of that paper simply do not have sufficient GPUs to train the models on the entire ImageNet. And even worse, the recent pure defense requires 1 to 4 high-end NVIDIA GPUs with 32 gigabytes of memory. And this is not some computing resources that are easily available for most labs, I think. And this problem is what we have recognized, but not yet developed a mature solution. And the second, the fundamental weaknesses of the defense remain unknown. For example, we don't know why randomness cannot provide robustness as we expected. and we don't know how future defenses could avoid the pitfalls of these defenses. So driven by these questions, we noticed that instead of investing endless efforts in designing complicated adaptive attacks, which is to prevent the attack, we should perhaps look for the defense's fundamental limitations. And this leads to the first limitation we found, which is the lack of sufficient randomness. For this limitation, we need to understand what do stochastic defenses look like and what are the core techniques used to evaluate them. So we formalized stochastic classifier as a mapping between from the input space to a continuous output space where we have C classes and D-dimensional inputs, and the randomness is characterized by a random parameter drawn from a randomization space. And to determine a prediction, we apply majority vote over n votes, where for each vote, we instantiate classifier with an IID sample random parameter. That is, for each vote, we will do one inference and check if that sample votes for class C. And as for the attack techniques, we have PGD, which is an iterative attack. And at each iteration, it will update the candidate adversarial sample with the gradient of some loss function and a fixed learning rate, all the step size. And another important technique is the EOT. And because the classifier is randomized, so the current evaluation wants to compute the expectation of the gradients. But in practice, the expectation is estimated with Monte Carlo sampling of M samples. Now, as we can see, EOT is the only technique that explicitly handles randomization. So if we want to study randomization in stochastic defenses, we should first understand how EOT becomes a core technique used to attack these defenses. For this, we will go through how the literature develops its view of EOT. So EOT was initially proposed for synthesizing examples that are adversarial to adversarial over a chosen distribution of transformations. And then it was adopted to correctly compute the gradient over the expected transformation to the input. And after that, it became a standard technique for computing gradients of models with randomized components. And finally, evaluations say that evaluations should explicitly detect randomized components and enforce the application of EOT for robust evaluation. And from this rightful development of EOT, we can see how seriously the literature has been treating randomization as a strong defense. But taking this too seriously can lead us to a blind spot. That is, we don't know the randomization security under weaker attacks. For example, let's consider a case study of the random rotation, which simply rotates the input image for theta degrees as a defense. As we can see that this defense is representative for most stochastic preprocessing defenses that in a way that it transforms the input image and it's randomized. However, when we attack this defense with different combinations of PGD and EOT, we find that standard PGD without applying EOT can already break the defense as strong as the advanced attack using EOT. And this observation implies that randomness can be insecure even under standard attacks without handling randomness. And pushing this observation one step further, we find that most existing stochastic defenses actually do not have sufficient randomness. For this, we extend the previous case study to a comprehensive evaluation where we revisit previously broken stochastic defenses and reevaluate them without applying EOT. And interestingly, we find that standard attacks already perform pretty well as long as they run for more iterations with a smaller learning rate. And for this evaluation, it's important to know that we only use the SAM code from the paper breaking those defenses, and we only chain their number of samples to 1 as a proxy for disabling the EOT. So this confirms that most existing stochastic defenses are not sufficiently randomized to the extent that they cannot even defend against the standard attacks designed for deterministic defenses. So this finding gives us a renewed understanding of randomization. First, we have a better understanding of why could we break stochastic differences. Before this study, we only know that we can break these differences because we applied EOT, but now we know that we can break them because they do not have sufficient randomness. And the second, we have a better understanding of security if we want to apply randomized defenses. And before the study, we do not have a clear answer when the attack does not apply EOT, but now we know for sure that these defenses are not even secure under standard attacks. So a follow-up question would be, what if the defense increased their randomization space, like the bar defense? And this question leads to the second limitation we find, which is the trade-off between adversarial robustness and model's invariance. For this limitation, we need first to understand what does it mean for a model to be invariant. A common definition is that the defendant model is identical to the original model over the randomization space and the input space. However, if this is the case, as we can see, if the defendant model is truly invariant to the defense, then attacking the defendant model will be the same as attacking the original model, which is straightforward by plugging the definition of invariance to this attack procedure. And this simple observation implies that stochastic preprocessing defenses are not expected to work, because if attacking the defendant model is no different from attacking the undefended model, then the defense would have provided zero extra robustness. So we then explain this observation with a toy example, where we consider a binary classification problem over a balanced data set of labels -1 and +1. And each class follows a normal distribution. We also consider an L infinity bounded adversary that perturbs the input with a small noise delta with perturbation budget epsilon. And we also quantify the classified's robustness using robust accuracy. That is the ratio of the correct predictions that remain correct after being perturbed. Or in this demonstration, that is the ratio of the dotted area over the shadowed area. Now, as we will show in 4 steps, why a stochastic preprocessing defenses should not work in this setting. First, when there's no defense, the optimal linear classifier will look at the sign of the input. That is, if it's on the right hand side, then it's +1. Otherwise, it's -1. And in this case, its robust accuracy will look like this. This is the baseline robustness without any defense. And here we don't need to care about its precise value, but only treating it as a baseline robustness. And next, we introduce a defense that adds Gaussian noise to the input. With this defense, the processed input will follow a new distribution, which is shifted by 1 to the right with a slightly larger variance. As we can see from the figure, the original classifier has less vulnerable data points, but more errors. And the robustness at this point will look like this. And we can formally show that it's higher than the previous baseline robustness. That means by introducing this defense, we have indeed improved the adversarial robustness, but at the cost of accuracy. And after that, we want to improve the accuracy, so we have to fine-tune the classifier on the processed inputs to preserve the utility. And this will lead to a new optimal classifier whose boundary is also shifted by 1 to the right. And as we can see from the figure, the classifier almost goes back to the undefended case. And its robustness will look like this, which is lower than what we have before fine-tuning, but slightly higher than baseline. And finally, recall that these defenses require majority vote to determine a stable prediction. So given this classifier that we derived from the last step, we need to apply majority vote over this classifier. And after that, we can prove this classifier will converge back to the original undefended classifier. And its robustness will also become exactly the same as the baseline robustness, meaning that after applying the defense and do the fine-tuning and majority vote, the defense provides no extra robustness. So we generalize this observation to a formal trade-off between robustness and invariance. And for this, we define the rate of invariance as the probability that the defended model makes the same assumption, the same prediction as the original model. And under this definition, we have theorem looks like this. That is, when the defended classifier achieves higher invariance to preserve utility, the adversarial robustness provided by the defense will strictly decrease. And we can visualize this theorem in the circle about stochastic preprocessing defenses, where we can start from the upper right corner that given the defense, we want to first increase randomness to improve robustness, hoping to improve robustness, but that defense will make the model variant to randomness, which will lead to lower accuracy. And if we want to improve the accuracy, we have to fine-tune fine-tune the model on that defense, which will make the model invariant to randomness, and finally leads to no extra adversarial robustness. And now we are back to where we started. We again want to increase randomness and only ended up with no extra adversarial robustness. So from this result, we can see that stochastic preprocessing defenses explicitly control the invariance or the model's invariance to provide robustness. So what does this mean? And what does it imply what stochastic preprocessing defenses really do? So first, it's clear that they do not provide inherent adversarial robustness to the model. And right now, only adversarial training, or not only, but adversarial training remains the most reliable way to provide inherent robustness. That is making the model truly robust. And in contrast, the stochastic preprocessing defenses only shift the input distribution through randomness and transformations. And this is an explicit control of the model's invariance. And what we observed of the adversarial robustness is only a result of the introduced errors. And right now we have only talked about stochastic preprocessing defenses. And there's a recent work actually generalized this message to a broader notion that for any stochastic defenses, the randomization may not help to improve the robustness. And this leads to the question of, so what are the more reliable applications of stochastic defenses? We know that randomized smoothing remains an effective framework for certified robustness. And this is a slightly different notion from improving the model's robustness. Here, randomized smoothing only certifies the robustness of a given prediction, but not to actually improve the robustness of the model. And another important application is defenses in the black box type model. In this case, the defender would need additional queries to infer the randomization space to increase their success rate. So the black box attacks would have slower convergence. And as for future research, a more reliable way of using randomness for improved robustness would be decoupling robustness and invariance. One example of this is keyword spotting. And this tag is inherently divisible in the spectrum space and force the attack to target non-transferable subproblems. And for example, in this case, if we do not apply randomization, the attacker would only need to perturb one single slice of the features. But after applying randomization, the attacker has to forced to perturb all the slices of features. And that means we need to avoid randomness that brings errors, but to apply randomness that will force the attacker to target non-transferable subproblems. So to summarize, we have discussed the standard preprocessing, where defenses must consider the whole machine learning pipeline to provide true robustness, and the defensive preprocessing, where the defenses should avoid randomness that brings errors and try to find new ways of using randomness. And this concludes my talk, and I'll be open for questions.
Thank you very much for US talk. Can you hear me?
Yeah, I can hear you.
Yeah, I have a general question. Just now, I typed it on my chat box. I kind of have a follow-up questions. Do you think it's hopeful we can have a ultimate solution to address the vulnerability in machine learning, or do you think there's no way to address it at the moment? So we need to think of other way around.
Right. So yeah, that's a good question. I think right now there are generally two regimes for protecting the machine learning model. Like one is to do adversarial training to actually improve the model's robustness by a outer loop, inner loop optimization. And the other is have some plugin as a defense to trying to prevent adversarial examples. So I think if we look at the adversarial training, then that might have more confidence because it's indeed a optimization solution that will reduce the space of adversarial examples. So I think that's a working case. But for the other plugin defenses, like for security regime, it's very hard to have an empirical defense that are proven robust. Because we can always see this cat and mouse game between attacks and defenses. So if we are not addressing the fundamental problem of adversarial examples, like using optimization or some certified defenses, then I think it's very hard to make a claim that an defense will not be broken in the future.
I see. But I personally do a lot of adversarial training research. But I find adversarial training research did have some problem. One key problem is they perhaps cannot protect the machine learning model from all the attacks. Kind of they only have some kind of limited protection, performance, and also other issues. So that's probably the reason why I asked the previous question. Yeah, I understand your meaning.
Yes.
What do you think?
So I think the point you raised is pretty good. Like right now, adversarial training still assumes that we know what the attack is, what the attack's algorithm at test time. That is, we do adversarial training using, say, PGD attack, but in our infinite norm. But at test time, the attacker can use L2 norm attack to like break our defense. So this is I think this is a research direction that people want to address. That can we have some matrices that we do adversarial training that will generalize to different norms? And I think that's a hard question, but I will have hope in that direction.
I see. Okay. Thank you very much for yes, great talk. We hope if you have time, you can visit our weekends Nihon Bashi's office physically in the future. Is in the Tokyo.
Yeah, sure, definitely.
Okay, thank you again. Okay. This is So hi audience, if you have other questions, you can email Yue Gao and to ask. Okay, thank you. All right. We're going to have our next speaker. Meanwhile, I will introduce Ming to our audience. Dr. Ming Ying is a PhD candidate at UCSD. His research spans a wide range of machine learning topics, including reinforcement learning, robust machine learning, Bayesian statistics. Ming serves on the program committees of several conferences, including NeurIPS, SML, ESDEX, UEI, and EEI. He's also area chair for NeurIPS 2023. He has spent time at Princeton University and Amazon AWS EI. Today, we are very honored and very happy to have our second guest, Ming, to give us his research towards sample optimal offline reinforcement learning. Hi, Ming, please.
Yeah, thanks, Jingfu, for the very kind and a nice introduction. And thanks to everyone for coming. It's really like a great pleasure to be here, talk at the Recon, the Trust Machine Learning Young Scientist Seminar. So briefly speaking, I'm Ming from UCSD. So I'm a PhD candidate from computer science. And today I'll talk about towards sample optimal offline reinforcement learning. So let's get started. Okay, so the question I'm considering is the reinforcement learning problem. So for those who are not very familiar with that, at a high level, reinforcement learning is really about you have an agent that can interact with the environment through taking actions. And based on each action that is taken, then the environment will transition you to a new state S prime and give you a reward function R. Then the agent can take the next action again, then this process just repeats. So RL agents learn at a high level, RL agents learns interactively through the feedback of an environment. Okay, so and arguably RL is among the hottest area of research in machine learning. For example, from the statistic in NeurIPS 21, it appears like 199 times, even more than the topics like deep learning. Okay, so while the exploration setting where interaction with the environment with the world is a very popular setting, however, for many high-stake practical questions in our real lives, we don't have access to such an online exploration. For example, trying to have a safe autonomous driving by driving off the road, it's a very dangerous and unethical, right? So therefore, reinforcement learning in practice always start with an existing data set, so which is what we call the offline RL. And in particular, there are two tasks in offline RL. The first one is called off-policy evaluation, or OPE for short, and the second one is offline learning, okay? So for both tasks, basically, you are provided with the historical data that is collected by some behavior policy mu that collects the previous information about the state, action, reward, and the transition to the next state. And your goal is to either evaluate the value of a fixed policy you care about. This corresponds to the task of OPE. And you could be asked to come up with a new decision policy per head. And this is what we call the offline learning task, okay? So to give you an example, think about the medical treatment problem. So for the medical problems, doctor has medical records of the patient's treatment and the outcome, okay? And based on this medical treatment, you can be asked to either evaluate a new treatment plan, that is OPE, and or try to come up better treatment plan from the existing data. So that is like the offline learning setting, okay? So for those type of tasks, you don't have a budget to do further online exploration. Therefore, all the successes you witness, for example, from a DeepMind, like the success in the Atari game, where they can achieve like superhuman performance, those algorithms will actually break for those high-stake practical problems, because we don't have a simulator where usually we don't have a very good simulator for those high-stake problems, and the sample efficiency matters a lot due to we don't have a simulator. Therefore, the scientific question we wish to address is that how many samples do we actually need to solve a reinforcement learning task? Let's say up to some accuracy. Okay, so that's really the scientific question I will be covered today. And I've been thinking about this for the past few years during my PhD study. Basically, there are two set of problems, offline RL and online RL. There are also intersection between offline and RL and online setting. It's called the so-called low adaptive RL. So In particular, in this talk, I'm gonna be discussing actually the offline policy learning task. So this is a this is small typo. So I'm gonna talk about this offline policy learning task, and we'll discover the three papers that is presented at the NeurIPS and the ICLR 2022 and 2023. So let me get to more detail. So to study how many samples we need for solving a reinforcement learning problem, we basically need to start from the most basic setting, which is the Markov decision process. And to simplify the problem a little bit, let's consider the very simple base model, which is the discrete Markov decision process. Okay. So a Markov decision process consists of discrete states and actions, and the horizon that is capital H. And at each step, you'll receive an instantaneous reward that is less equal to 1. And the transition will transit the current state action to the next state. And you have a behavior policy. That is, the policy collects the historical data. We'll give you the action that is sample from the historical policy mu, and each policy will induce a visitation measure. And here we use this notation d mu of t. So this is nothing but just the marginal probability of attaining state S and action A at particular time t. Okay, so this really represents a marginal distribution of state S and A at time t. Okay, based on those notation, we can define the value of a policy, which is a expected cumulative reward under the certain policy. And based on that, we can have the standard definition for V function and the Q function, which is also the expected cumulative reward, either conditional on the current state or the current state and actions. Okay, so to give you more illustration about that, the MDP usually starts with the initial state, and you have a policy, which is a behavioral policy here in the offline regime. And the policy will give you an action, which is A1. Then based on that, the word will will give you an instantaneous reward R1, and also transition to the next state, S2. And based on that, you need to choose a policy again, which is A2, and obtain the second instantaneous reward R2, and this process just repeats, basically, up to some time capital H, okay? And the value is measured by the expected value under the policy pi. And the interesting question in reinforcement learning is we actually want to find a policy pi star such that this value of V of pi is maximized. So that is really our goal. And if you simply want to do that, and if you know how the world behaves, which represents this transition dynamic, then you can simply apply the dynamic programming principle to solve this problem. And if we'll give you, especially in the tabular case, you'll get the optimal value perfectly, okay, via this iteration, okay. And usually, like for real world problem, we don't have knowledge for this P of H. And in addition to that, we call a policy pi is a epsilon optimal policy if its difference with respect to the optimal value is bounded by epsilon. Okay, so this is the setting. Let me give you some concrete examples. For example, consider this simple 3 states MDP. Okay, so for this simple 3 states MDP, it is very easy to tell that the optimal policy is to take the action left, right? Because in that case, if your horizon is 100, it will give you the reward 100. Otherwise, if you choose right, it will obtain a 0.1 suboptimal policy. Okay, this is like a very simple example. How about the Super Mario one? So can you tell me like how to get a 0.1 optimal policy for this Super Mario game? So this is a very difficult question, right? So I saw a question from a chat, which I believe is for me. So is there any requirement to the data set like IID? Okay, this is a great question. So it depends on the specific situation. So yeah, actually refer to what I'm gonna talk about here. So let me just continue. I will answer this question automatically. So for here, if you want to solve a Super Mario game, you cannot like directly know what is, for example, even the 0.1 optimal policy. Therefore, we need to learn from the data. Okay, that is what reinforcement learning about, because you don't know how the real world actually, the real world transition is, and all we have is historically collected data set. Okay, and I think the question from Xiong is, do we require ID assumption? So so for the from practical perspective, it is okay that data are not IID samples, and you can run different type of algorithms such as actor critic algorithm or policy gradient type of algorithm. They have like pros and cons themselves, but from the statistical perspective, from the analysis perspective, we will assume here all the trajectory, they are independent trajectory sampled by a policy, but within each trajectory, they are not IID. For example, you have a state sample from S1 and A1, then the next state, S2, will actually depend on the S1. So within the trajectory, they are not IID, but across the trajectory, they are IID. So you can think about this as playing a Mario game, like 1,000 different times. Then across these different tries, they are independent plays. But within each play, they are actually like correlated with each other with respect to the time. Hope this answers your question. Okay, so that's an example to show you that like for many problems, we need to do from a data-driven perspective. Therefore, the goal of offline RL is really like you have a historical data and you try to come up with a policy pi hat, such as just very close to the optimal policy. Okay, and that is our goal. So actually, offline RL is a very hard problem because in a lot of cases, you actually need to learning from a suboptimal non-acceptor data. So for instance, it is very likely like the observed trajectory is the upper road for this robotic, which actually give you nothing with reward 0. However, what you actually want is something in the lower road, which give you a very high rewarding outcome. Okay, so this means that the data distribution mu, which is something tried by previous agents, might cover a space that is never visited by the optimal, the best policy you can have, right? Therefore, a very important question in offline reinforcement is to tackle such a distribution mismatch. Okay, and from previous literature, there are different ways, or it's better to say different assumptions people made to characterize such a distribution shift. For example, the first one is called a uniform data coverage. So if you recall that this notation d mu of t is the probability distribution that attain certain state and action at a particular time t, then this uniform data coverage assumption requires this quantity to be positive for any state action at any time t. So this is a pretty strong assumption. So intuitively, this is basically saying, okay, your offline data can explore all the possible state action you can have. So it basically says, have seen all the knowledge you need for solving this task. Therefore, learning is slightly easier in this setting. Okay. And the second one is a partial data coverage assumption, which is also very popular. Instead of making assumption that the behavior policy, the marginal distribution induced by the behavior policy covers all the state action spaces, it only requires it covers the state action space that can be visited by a particular optimal policy. Okay, so this is a difference between those two, because some optimal policy might only explore a subspace of the whole state action spaces. So if that is the case, in order to learn the optimal value, we don't really need the historical data to cover all the spaces, but rather just cover the spaces that achieve the optimal value, then we are good. So this is a qualitatively a weaker assumption than the uniform data coverage. Okay, that's something people considered previously, and based on those assumptions, there are some nice statistical guarantees for studying this suboptimality between the for offline RL. For example, there are some techniques called minimax, Bellman error minimization, can give you an error rate such that the value of B of pi star minus the value of B of pi hat can be upper bounded by this ratio. This number of samples you have, the number of trajectory you have. And if you under uniform data coverage assumption, then this bound can be bound of square root of h cubed over n times dm. Okay, so you can forget about all those technicality and just remember that, for example, for the second rule, this guarantee, this order is actually minimax optimal. So what does this mean? This means in the worst case, there's no algorithm that can actually beat this rate, which means this is roughly the number of samples you need to suffer in order to learn an accurate optimal policy. Okay, so that is like information theoretical that nearly matches the lower bound, so which is pretty cool. Okay, then what else do we need to do? They are already like optimal in some sense. Okay, so let me give you an example to think about what is missing. So for example, for the 0.1 optimal policy, if we translate that minimax bound, we will have this n is roughly of order h cubed over the parameter d of a. Okay, and for the Super Mario game, you say you want to play it for 1,000 steps, then you can, and this is the minimum of the visitation, marginal visitation probability. So it is less equal to 1. So if you plug in this dm equals to 1, h equals to 1,000, you can easily calculate it roughly requires like 10 to the 9 sample to solve a pretty like challenging problem. Okay, but if you reduce to the much simpler 3 states MDP problem, we know that we only need 2 samples to solve it, right? We just need to try the left and try the right respectively. Then because those 2 states 2 and 3, they are absorbing. So we already know that the left is the optimal policy, even though we are considering the same horizon, that is 1,000 steps, but we don't really need that because this is a much, much simpler problem, right? So that tells that the minimax bounds also is the worst case bounds. Their prediction is usually much larger than what is actually needed, right? Because they always give you this prediction for all the problems. However, different practical problems have different hardness, and a simpler problem is easier to learn. So while this worst case guarantees is nice, they do not reflect the nature of the hardness of the individual problems. Okay, so that is our goal. We want to ask like the performance of many problems are far better than what those worst case bounds would suggest. And they need to separate analysis with different assumptions So the question we ask, can we achieve the results that explicitly describe the sample complexity for individual instances that can also imply the existing results? So our goal is like twofold. We wanted it to be can subsume the existing results, but meanwhile we also wanted to hold can characterize the hardness of individual instances. Okay, so that is our goal, and based on this, we derive what's so-called the intrinsic offline learning bound. Okay, so far, if you like didn't get anything else, that's totally fine. So what I really want is you can focus on this slide and understand the main message. So that's the main contribution of this talk. So what is the saying is that under the partial coverage, which is a weak coverage assumption, we have with high probability, then we use an episode of offline data set, we can output a policy pi hat such that the gap between our algorithm and the optimal value is bounded by this complicated measure. Okay, this looks a little bit intimidating, so let me help parse it to you. So first of all, it is described fully by the system quantities, that is the marginal distributions and the conditional variance terms, which does not explicitly depend on the worst case parameters such as S, H, S, and A, like previous paper did. Okay, and if you look at those two, those d pi star over d mu actually is a distribution mismatch ratio. So this tells you that if the two policies, if your behavioral policy mu is differ a lot from the optimal policy, then this quantity will be intrinsically larger, right? Which also means it's a very hard problem to learn. And on the other hand, this conditional variance is what we call the environmental variations. This is a critical component because it measures like how hard the transition dynamic with respect to the optimal value. So you can see that for the stochastic problem, this value will be higher. And if you have a deterministic transition, then the variance will automatically be zero. So that means, so this theoretical guarantees intuitively tells you, verify from the theoretical perspective that the learning hardness for the stochastic problem is much larger than the deterministic problem because of this environmental variation measurement, right? And combine this two, this characterizes the hardness for the individual problems. So that depends on concretely on the transition probability and the ratio between the quality of data set, which depends on mu, and the optimal policy of the Markov decision process. Okay, so that's the main message. Tells you that the learning hardness is a mixed effect of distribution mismatch and the environmental variation. Okay. So let me further give you some corollaries. So first of all, we can nicely subsume all the existing results under their respective assumptions. So maybe I can go through this page really quick. For example, if we consider the uniform data coverage assumption, then we can bound this term by Cauchy-Schwarz inequality twice and a law of total variation. We can see that this complicated measure can be actually bounded by the rate of H cube over NDM, which is a worst case guarantee achieved by the previous paper. Okay, we will get that for free without any change. And we've already seen that in the worst case, our guarantee can imply H cube over NDM sample complexity. Then we want to know how about the simpler problems, right? So let's go back to this 3-state MDP, for example. And in addition to that, let's assume that the initial state have a uniform distribution over two actions, and the reward is simply standard normal reward. And in this case, since this state 2 and 3, they are observing states. Therefore, the environmental variations for h greater equal to 2 will simply be 0, right? And in this case, the complicated measure, which is what we call the intrinsic offline learning bound, will reduce to a measurement that only sum has a summation over the first term, okay? And by a simple calculation, you can find this is a square root 2. Okay, so this is only constant sample complexity for finding the 0.1, does not scale with h. Okay, so recall that the worst case always predict that the sample complexity has this order. But based on our intrinsic offline learning bound, if you specialize to a particular problem, it automatically gives you some prediction that is correct, because it's adaptive to the respective particular problem. Okay, that is nice. And one more example is about a fully deterministic problem. For example, if you think about the lunar lander game, which is you have a robot that are trying to land in between the region of these two flags. And this is deterministic because every time either you go left and go right, then the location, which is your state, is deterministic, okay? Then in that case, you have this environmental variations to be 0 for all of h. Therefore, this complicated measure reduced to the bound that is of order 1 over n. Okay, this is very nice because the minimax results always have a square root 1 over n convergence, which is standard statistical parametric rate, if you're familiar with statistics. So this tells you we can have faster convergence for some specialized system based on our guarantee. And we have all of this property for free without any like extra tune or anything. So that's the reason why our result is strong. So to summarize a little bit, we directly subsume the previous worst case guarantee result with the instance dependent results. And under a specific regime, we have a faster convergence property. Okay, so to best of our knowledge, is the strongest near optimal instance dependent result in offline reinforcement learning to date. Okay, so now it is your turn to wonder like what algorithm actually gave this strong guarantee, right? So that's what I'm gonna explain next. So before that, let me actually tell you a principle that is pretty general, does not only coupled with this particular problem that can be applied in a more general way. So this is a principle called a pessimism in the face of uncertainty. Okay, so let's think about the problem like how much can we trust an estimate Q of head using a dataset D? Like, yeah, you can use any way to use a dataset to estimate, for example, a Q function. And because the dataset will have different coverage at different locations. At some locations visited more and at other locations have less visitations. Therefore, they will have different uncertainties at different locations, okay? That is a fact. So therefore, which means we can use a measurement to calculate the uncertainty in a particular state and actions, okay? And in the online case, if we can interact with the environment, we like the high uncertain state because we have the access to explore with the environment to further reduce the uncertainty. And in the offline regime, we are provided with a fixed historical data set, and we can no longer do the exploration. Therefore, we don't like it. Therefore, how should we modify the original estimate of Q hat? It is to a conservative estimation, right? Because if you have a particular location that is very uncertain, because we are considering the offline regime, we don't have exploration, then we tend we cannot trust the estimate value too much. Therefore, we penalize that by subtracting that value with respect to the uncertainty measure. Okay. So, and if the at a particular state and action, the uncertainty is very, very low, then we're more certain about that the estimated Q value is good. Therefore, the penalty will automatically be very small. So, so that is updated Q value based on the principle of pessimism. So this is a very generic tool that can be applied in a broad range for the offline problem with uncertainty involved. Okay, so that's also the way how I'm gonna design my algorithm for the offline reinforcement learning problem. Okay, so let's start from the Bellman optimality equation. Okay, and here we don't know how the word transition is because this is unknown, but it's fine. We can use a data set to approximate this transition via empirical count because we are considered the simple tabular setting where we have a finite state action. Therefore, we can construct the empirical transition estimate, and we can simply plug in here and get approximated Bellman equation. Okay. And but if we stop here, we didn't really take in count into those distribution mismatch problems and under coverage part. Therefore, we need to use the principle of pessimism to measure the uncertainty and to do the modification of the approximated Bellman equation. Okay, so this is the uncertainty measurement we designed. It consists of it controls the uncertainty in two parts. The first part is this quantity NSHAH in the denominator. So this number is basically counting like how many times you visit the particular state action. So if you visit more, you are more certain about this location. There, the uncertainty is low. Okay, that is intuitively why it makes sense. And the second part is the empirical conditional variance in the numerator. So that actually measures the intrinsic hardness of this problem. So if you have a larger variance, if your transition automatically have a larger uncertainty at particular state and action, then it is automatically hard to learn, no matter like how many samples you observe at this location, right? So this is actually a delicate choice. On the other hand, it cannot be bigger because if you make this bound bigger, then this is very conservative estimate when you subtract this with respect to the estimated Q function, and the bound will be loose. And it also cannot be smaller. If it's be smaller, it will break the principle of pessimism. For example, if you simply took this to be 0, then you are not penalty anything. You're not applying this principle of pessimism. Okay, so because of this delicate choice, we can come up with our final algorithm, which we call the adaptive pessimism value iteration. Okay, so the algorithm is pretty simple actually. First, it's just compute the empirical estimation of this p hat, then just do the value iteration with pessimism. Okay. And in particular, it applies the approximate Bellman equation and the adaptive pessimistic design I just explained in the previous slides. After that, you can compute the V function through the greedy policy update. Okay, so this is the reason why I like it, because it provides a strong theoretical guarantee, but meanwhile, the algorithm itself is pretty simple. We don't apply fancy techniques like, for example, like advantage decompositions or the like variance reduction techniques used in previous paper, but it achieve very strong guarantee that tailors to each particular instances, but also recover the previous results. Okay. So do you have any questions so far? Okay. So let me continue. So far, all I talk about is a tabular setting, which means you have discrete number of state and actions. So it is easy to argue that those type of scenarios far from practice, because many practical problems, they are continuous problems. And this is what I'm going to talk about next. So this make a lot of sense, because, for example, if you play the Super Mario game, if you saw a red mushroom, you know it's good. Then next time you saw a green mushroom, it is easily to guess that it might be good as well, right? Therefore, we need some like functional approximation tools to generalize to unseen states. So that is what we, and the particular scenario we consider here is a linear functional approximation. So concretely, it is function class that model the Q function as an inner product of a known feature map with respect to a vector in the R of D. Okay, therefore it's a linear in the feature and in the weight as well. So actually, this linear function approximation is frequently used in practice, for example, of the games, and it works quite well. So, and in addition to that, we need assumption called a linear MDP that states the Markov decision process can be modeled by with a low rank structure. Okay, so it's this D is its factor. It can be modeled at a low structure, and with those type of settings, it can help generalize the previous discrete case to the continuous case. For example, if you instantiate this feature representations at the one hot indicator of the state and action, and choose the dimension D to be the number of states multiplied by the number of actions, then automatically go back to the previous tabular case. Okay. And if I can go back, one particular scenario for how to design this feature phi is to, for example, for this Pac-Man game, you can design to be like how many distance is it from your Pac-Man to the ghost, and what is the distance from you to the nearest food, this type of thing. So you can obtain a known feature map. Okay. And the statistical question we want to consider is under this setting and under some data coverage assumption, which means our behavior policy mu can explore all the D dimensional of the feature representation. Under this case, how can we do offline reinforcement learning? Okay, so the setting is again that you have the offline data trying to learn policy such that is epsilon optimal with respect to the optimal V function. Okay, and we want to know what is the smallest sample we need, what is the optimal sample complexity we need in this scenario. This is much more challenging than the tabular case because we are dealing with continuous representations. So instead of directly explaining like how to achieve the optimal sample complexity, let's first say how to solve it in the polynomial time. Okay. So recalling the standard supervised learning, the popular way to update the parameters via the square loss function, right? And therefore, in reinforcement learning, people also leverage this type of least square regression idea to propose the algorithm called least square value iteration. And it's exactly this objective. So if you recall this inner product between the feature of the weight as a function with respect to your linear function class, then this Bellman target will correspond to the signal yi, and the goal is to simply to do a ridge regression and update the value, and that will be your estimated Q function, W hat. Okay, so this is nice because this is kind of a default choice for the linear type of regression problem, and the nice thing is it has a closed form solution, so it's easier for the analytic purpose. However, this type of algorithm is not sample optimal. Okay, so that is what we want to address here for this problem. So concretely, if you think about the linear regression, you're familiar with statistics, then you know that they require assumption that the noise is their IID noise, okay? And if you have this IID noise, then you know that, then you know that for the fixed design linear regression problem, this is the statistically optimal. Okay. So the least square value iteration is mimicked this way by simply doing this ridge regression thing. However, the biggest problem is the noise in the reinforcement learning, they are not identically distributed. Okay. So what does that mean? So it is easy to understand from this visualization, because if you start from different state actions, then the probability transition distribution, there are different probability transition distributions. They are defined separately, therefore it could be infinite many number of transition probabilities, then you're regressing them with a single objective. So there's no way for it to be optimal. And this is due to that reinforcement learning is heterogeneous in nature, because different state action corresponds to different distributions. Therefore, the samples with low variance in transition is much more informative than others, right? If you have a sample that have high variance, you don't want to treat that as the same sample as a sample that have a very low variance. Because if you have a sample that has low variance, you're more likely to observe this value. So, however, if you look at this objective, they weight all of them with the same weight. Therefore, instead of doing the least square value iteration, what we did is via a weighted least square value iteration. And conceptually, the idea is similar to the previous tabular setting by reweighting this objective where uncertainty measure, which is conditional, estimated conditional variance. Okay, so how would this work? So it actually works, and it will give us the optimal results in the linear function approximation regime. So comparing to the existing algorithm, they use a least square regression plus the principle of pessimism. And what we did here is we first compute the conditional variance, which is uncertainty measure, and we put it into the regression objective and obtain the variance aware regression, and also apply the pessimism principle. And based on that, we can achieve again the instance dependent oracle inequality for the linear function approximation as well. So it's a little bit complicated measure, so you don't need to. I don't want you to look at the detail of these formulas, but all you need to know that it's a key preserves the similar feature as what I explained in the linear case. For example, the distribution mismatch and this environmental variation. So it is much more adaptive than those worst case bound in the offline regime. Okay, and it nearly recovers the previous result when we restricted the feature representation to be one hot encoding and the feature dimension D to be S times A. Okay, so speaking of the effects of pessimism, we also run a simulation to show that it actually helps if we put the appropriate pessimism strengths. For example, in the update, this beta of k is the strength of the pessimism. So, and if you look at this figure, when it is properly chosen as 1.0, then you'll find this yellow line have a very fast convergence comparing to the non-pessimistic version, where this beta equals to 0, right? And this phenomenon does not change when you change this problem to the longer horizon problem. So you can still say that with a proper choice of pessimism, it actually improves the performance of offline reinforcement learning. Okay. And this roughly provides a complete story in understand the statistical limits, the sample efficiency in the offline area. So the first part I explained the discrete tabular RL, which has this complexity measure that is near optimal and instance dependent. Further, for the functional approximation regime, we achieved something similar. And in the most recent ones, we consider the general parametric functions, which means instead of assuming this Q function is a linear function, we allow it to be any arbitrary generic function that is differentiable. Okay, then we can recover a similar complexity measure such that offline learning is still efficient. And it covers a broad set of functions and algorithm that works well in practice and build the theoretical foundation for that. So this line of my research has been actively followed by other groups. Okay, so if we think about this like a variance or reweighting scheme, it's pretty generic, right? For example, if you every time you have a square error loss for the regression, you can always do some type of a reweighting, and it automatically give you a like new algorithm, right? However, if we can design such a sigma I, which is uncertainty measure, in the principled way, then it is likely your result can like outperform the vanilla version with the square error loss. For example, this type of idea has been applied for the autonomous driving in this paper, and you can like try to brainstorm a little bit for other sequential decision making applications. This type of uncertainty measurement and the reweighting scheme might be helpful because we already witnessed its effectiveness for the like offline reinforcement learning task. Okay, so the take-home message is really like the principle of phase of uncertainty is a generic principle that works well in the offline regime. And the learning hardness is a mixed effect of the distribution mismatch, which is a mismatch between the historical policy mu and the optimal policy pi star, and also the environmental variations. If the problem is a stochastic problem, then it's usually harder. And if it's deterministic system, then its degree of freedom is smaller than the stochastic one, then the easier problem is characterized by our like learning bound. And we can further generalize to the continuous case and explain the behavior of more complex problems. Okay, so I hope like this makes sense to you, even though you might not know the details of the formulations and their meanings, but you can at a high level at least understand like those are the things that matters to characterize the learning hardness for the sequential decision-making problem. Okay, so, and my general interest risk, which is other part in addition to my existing endeavor for the building the statistical foundation for reinforcement learning includes, for example, the robotics. And this is a recent manuscript that I finished with my colleagues and friends, where the goal, it is still considered the offline RL setting, and the goal is to work on the OpenAI module tasks, and we try to beat the existing benchmark methods for in the offline RL regime, and we work on the we compete with the we utilize the D4R dataset and propose what we call the closed form a mixture Gaussian policy improvement operator. Is a purely empirical work, and it outperforms a lot of existing strong baselines, such as the decision transformers and the conservative Q-learning CQL. And we perform the rigorous statistics test to show our empirical performance improvement is significant. Okay, so and AI for health. So for example, there are public data set that is available, and we can think about trying to use the medical predictions treatments with electronic health records. For example, this is a data set called Mimic3. It records the information of the patient's ICU stay. and you can formulate like this irregularize time series as a sequential decision making problems, and try to apply any like a RL machine learning algorithm you'd like to try to come up with a better treatment. For example, like a policy gradient or other algorithms. That's something I'm working on nowadays. And the next one I really want to mention is that due to the success of the large language models nowadays, it's very important to look at, for example, the GPT-4, ChatGPT, where inside their algorithmic design, one key component is to use a reinforcement learning with human feedback, right? So based on their technical report from the OpenAI, it's not very clear how exactly what they did in detail. So at a high level, they basically train a reward model based on the performance ranking as an input, and use that reward model as a reward to train a PPO algorithm. Okay, so therefore it would be interesting to understand how RL would actually help, for example, for a large language model in a principled way, and its preference-based feedback really better than others. Those are interesting questions to look at. Okay, so that's it. So this, yeah, the work I explained contains my joint work with my advisor Yu Xiang, who is from UCSB Computer Science, and Meng Di from Princeton, ECE, and Yachi, who is currently at MIT, but will join the NYU Stern in this fall. Okay, thank you so much. So that's all. Feel free to shoot me any questions.
Thank you so much for this quick talk. I have a general questions on reinforcement learning. So right now, even the ChatGPT or even many machine learning models, they don't know why they make such predictions. Kind of like they don't know the reason. Do you think that reinforcement learning is a way of helping the the machine learning model to become to understand why if this machine learning model makes such a prediction?
Yeah, that's a very good question. That's something I'm also super interested. I think one thing, it's hard. I would say like at the current stage, the most success of RL is for games, right? For example, the game of Go and the Atari games, they're like super strong competitors. One of the reason for that is in those type of scenarios, the design of reward is fixed. It's very easy to define what your reward is, and you're trying to like improve, maximize reward towards that goal. However, like practical problems, they are very complicated problems. It's very hard to define a reward that can satisfy everybody's needs. So it's very abstract. Therefore, for many problems, people usually find it hard to define concrete reward objective in a singular. Therefore, they cannot apply like reinforcement learning in a very principled way. Therefore, I'm interested in like how could, for example, the ChatGPT train this reward model such that it gives them a very good metric to measure like what is the score I should give you for a sentence or a response to a question, right? That is a very challenging question. Even you use people to annotate the question, they cannot usually give you a perfect answer. But if RL can play as a role to even, for example, even automatically give you the reward information, then that can help you to save a lot of human laboring, and also like have the potential to make more significant in understanding how the language models actually helps solving real tasks. Please let me know if I don't.
Thank you very much. Yes, indeed. Your answer is perfect. It's really helpful. All right. Hey, audience, if you have further questions, you can also email me to ask more about his research. Hi, Ming. we appreciate again for your today's great talk to our Rican people. Thank you
Thank you
very
so
much.
much. It's nice to see you all.
Yeah, yes. When you have time, please visit our Nihonbashi office in Tokyo.
Yeah, sure. I'm happy to do that.
Physically.
Thank you.
Thank you. Then this is the end of today's seminar. Bye-bye.